So I usually don't start my lecture with a commercial, but I am going to in this case. And here you go. Let me unplug this to make sure.
We asked people a question. How much money do you have in your pocket right now?
I have $40.
53.
21?
Do you think the money in your pocket could make an impact on something as big as your retirement?
I can't. No,
Probably not.
It's hard to imagine how something so small can help with something so big. But if you start putting that toward your retirement every week, let it grow over time, for 20 to 30 years, that retirement challenge might not seem so big after all.
So let's see. Last domino was actually a world record breaker. It was over 30 feet tall and weighed 2 tons. Now keep in mind, it was set to motion with that tiny little domino that said $43 at the beginning. And the reason I like this is it shows you in a very visual way exponential growth. And in this section, we're going to work with exponential functions. So the relevance of this here is that if you invest your money in a bank account or someplace that gets regular interest and regular growth, then likely it's going to be growing exponentially. In fact, Einstein said that one of the most powerful forces in the universe is compound interest. So, wow, pretty cool. So let's spend a little time getting used to this formula. So this is what I typically refer to as simple interest. That is, interest that gets compounded every so often, like monthly or quarterly or even daily. So let's see here, section 4.1. And let me write down our formula here for us. So it's A equals P times 1 plus R over N to the NT power. And P is your principal. That's not the person who would paddle you in first grade when you did something wrong. That's how much you invest initially. R is your interest rate. N is how many times a year the interest is compounded. T is time in years, of course. So let's take a look at this first one. It says if $300 is invested at an interest rate of 8% compounded quarterly, then the investment after 4 years is worth what? So let me copy down a few things here. First of all, P is 300. R is 8%. And then, let's see, T is worth 4 years. So, okay. I think I got everything I need. Yeah. Let's take a look here. There you are. Now, if you plug it in without too much thinking, you're going to get this thing wrong. Because your interest rate has to be expressed as a decimal. So what's 8% as a decimal? 0.08. And I'll go back and take a quick look at things and see what happens if you use 8 as opposed to 0.08. So I think it'll make a fun difference for us. So our formula for this one is going to be 300 times 1 plus 0.08 over, oh, you know what? There is one more thing I need to know here. And that is, how often is this compounded? Compounded quarterly. So quarterly means 4 times a year. So 4 times a year, they're going to give you some of your interest and dump it into your account. So N equals 4. And then raise this to the N times T power, 4 times 4 again, like that. So that's going to tell us how much is in our account after those 4 years under these conditions. So let's put that into our calculator. And the trick in putting this into your calculator is to not hit the equals button until you're all done. So let me clear this out. Start from fresh. Type in 300. Now on the graphing calculator, if you're putting a parenthesis here, it understands that they're multiplied. So you don't have to put in the times there. 1 plus 0.08 divided by 4, parenthesis, and again, do not hit the enter key until you're all done. Then I want to raise that to the power of 4 times 4. Well, you can either do 4 times 4 in your head and put in a 16, or do 4 times 4 like this. If you're getting a little caret here, as opposed to just an exponent, then you're going to need to put that 4 times 4 in parentheses, or just write it as 16. So we end up with 411.8357. So we need to round that. Where's a good place to round this? To what decimal place? Hundredths. Yeah, hundredths. Because the lowest unit of currency we have in our United States here is pennies, which would be the hundredths place. So I'll expect that you round these things appropriately. $411.84. Hey, that's how much it's worth. So how much in interest did you earn? Well, you start out with 300, you have 411.84. So the difference, 111.84, that's how much you earned in interest. So great. Now, good luck getting 8% on your investment. It's just not going to happen around here. Not anytime soon, but let's take a look back and see what happens if you forget to convert the 8 to a decimal. So I'm just going to hit the second key, then the enter key. That'll pull up my last calculation. And I'm just going to go through here and delete, delete. So there you go. I deleted the decimal, so now it's 8. Effectively, I'm giving myself 800% interest. So watch what happens to my $300. Wow. That's a number in scientific notation. So it's 1.2914 times 10 to the 10th is essentially what that is. If you want to unravel that a little bit more, that's going to be 12914,000,000. There you go. A little bit less than $13 billion. Effectively, I'd be retired if there were such an investment. I'd be on my own island someplace in the Pacific, you know, solving math problems just for fun. All right, maybe not the latter, but, you know. In any case, hopefully, if you see something like this, you go, well, something looks a little wrong. Okay, because it happens all the time. But it's not very likely you're going to start out with $300 and end up with $13 billion. Okay, so that's an example of exponential growth. Let's look back and see some more things. Now, let's see here. One of the things you're going to be asked to do is to actually just find some values. So maybe it's not a bad idea to practice that. We just finished working with our tables, so they're all set up. Let me remind the viewer here that if you hit the second key, then the window key, you want independent set to auto, independent set to ask, dependent set to auto. With that, let me go in here and type in some equations. Type in 1 divided by 5, parentheses, raised to the what? X plus 1 power, I think it was? Yeah, x plus 1 power, x plus 1. And now I can fill in anything I want. I can find to the first power, to the square root of 2 power, whatever I need. So we'll hit the second key, then the graph key. That gets me to my table. I need 1/2 square root of 3, negative 2.5, and negative 1.5. So let's try plugging in all those things there. So the first one was 1/2. Second one was the square root of 3. Oops. Square root of 3. negative 2.5, and negative 1.5. Now all you have to do is be careful rounding these things as the problem asks to the number of decimal places that they're looking for. I don't know what that would be in this case, but if when you look at your calculator, you're like, oh, wait a minute, I'm supposed to round to 4 decimal places, it's only giving me 2, like in this third one. Here's what you can do. Cursor up here and put your cursor over that value, and then on the bottom of your calculator, you'll have more digits than you know what to do with. So you should be able to get whatever you need out of this. Okay. Now, all these are examples of exponential functions. So let's take a look at exponential functions and really try and understand them a little bit more. So that would be stuff like this. And let me make it a little bit easier to see here. There you go. Let's just do this. Let's do 2 to the x power. This is a very, very fast growing function. If you look at some of my other videos on my YouTube channel, what you'll see me doing is I'll graph this in centimeters. And then say 2 to the 2 centimeters, that's 4 centimeters, 2 to the 5, that's 32 centimeters, etc. And then I start moving up from there. At 10 centimeters, I'd have to stand on the height of a 3-story building in order to graph things, just doing it in centimeters. At 20 centimeters, that's less than the length of your arm. To graph the point on this graph, if this was all in centimeters, so let me kind of zoom out a little bit. If I was measuring from here to here, this point would be 1,048,576 centimeters tall. That's about 6 miles. It's a little over 6 miles. So, wow. The short answer is that these functions grow really, really fast. Now, that c here is the base of your exponential function. And there's 3 things about the graph of the exponential function that I want you to know. So exponential functions. Y equals b to the x. So the first thing is that, well, let's see. We're going to assume that b is greater than 0. In fact, it's a requirement that b has to be greater than 0. If b is greater than 1, then the function grows really quickly. It just takes off. Exponential growth. In fact, I used to rely on a bunch of other things for exponential growth to demonstrate that, but I changed, or I can change now, because there's another example of exponential growth that we've been dealing with for the last 2 years. Does anyone know what it is? COVID, yeah. Number of cases due to COVID. We've had 3 different spikes of COVID, and in each case, those spikes can be modeled by the graph of an exponential function. All right, so that's one thing. These grow really, really quickly. Another thing, let's remind ourselves, how do you find the y-intercept of a graph? You remember how to do that? Yeah. And if you set x equals 0, b to the 0 power is 1. So all these graphs, any graph of this form has to pass through the point 0, 1. And again, if b is greater than 1, then for x less than 0, so there's negative values of x, the graph approaches the x-axis. In other words, line y equals 0 is a horizontal asymptote. It gets close to but never touches that line. And I'll give you a second to copy this down here, and then we'll take a look back at our graph of 2 to the x and see what that looks like. It doesn't matter, because if b is between 0 and 1, it's still going to be something to the 0 power, and something to the 0 power is always going to be 1. So that point should be on your graph regardless of the size of b. That's a great observation, though, and I'll try and point that out as we look back on our graph. So I put in c equal 2. Here's the graph of our function. Let me kind of squish that down a little bit. What if I had a different base? What if I had a base of, say, 3? Well, you're going to get the same kind of shape. It's just it's going to grow faster. Your function is growing faster. So if I put in a 4 here, again, it's growing faster. So that's what's happening with these functions. Let's see, down here. There we go. So I'll spread that out a little bit. So 2, 3, and 4. And you can kind of figure out the trend. If I put in, say, a 6 here, it's going to be taller than the rest of them, etc. Now, what if I had something, these are all numbers that are greater than 1. What if I had something less than 1 as my base? So what if I did, say, 1/2 to the x power? So if I looked at y equals 1/2 to the x power, well, another way to think of that is 2 to the negative first power raised to the x, or if I just multiply these, it's 2 to the negative x. So these two are identical. So I can have a negative exponent or something less than 1 to a positive power. Either way. But the bottom line is, when I turn on these graphs, I get the mirror image of these graphs. So on the one hand, you get exponential growth. On the other hand, you get exponential decay. So these numbers start out really, really big, and then they decay. On the other hand, these start out really, really small, and then they grow really, really quickly. So you can get either type of behavior. But back to your point, Samantha, take a look at all these graphs. All of them. I mean all of them. Pass through that point, 0, 1, right? So beautiful, beautiful. Now, part of what I'm going to want from you guys is the ability to shift graphs and work with shift graphs and understand what they mean. This handout is on D2L. Bless you. At least it should be. If it's not, let me know. So let's take a look here. My goal for you is to be able to describe what some of these graphs are and match up some of these graphs with these here. So let's start with 2 to the x. Well, the basic shape that you should get used to is one of these 4. So which one of these 4 do you think lines up with y equals 2 to the x without taking out your graphing calculator? Yeah, the third one. It passes through 0, 1, it grows really quickly, and it decays and gets close to but never quite touches the x-axis. Great. So that first one is 3. So let's see. 2 to the x is number 3. How about 2 to the negative x? Let's take a look at that one. So 2 to the negative x, there's a couple ways you could think of that. One way is you can think of it as 1/2 to the x. Another way you can think of it is by plugging in this negative x, you're reflecting your graph around the y-axis. So try imagining picking up your graph and spinning it around the y-axis. Which of those remaining 3 graphs kind of looks like that? where you picked it up and spun it around, you reflected it around the y-axis. 1, 2, or 4? Any guesses? Any guesses out there in the audience? No? 1. Yeah, thank you. 1. All right. So 1. So you can view this one of two ways. You can think of this as x to the 1/2, which is smaller than 1 for its base, so it's a decaying function, or you can think of it as being reflected around the y-axis. So you take this point and you put it over here. You take this point and you put it over here. You get the first one. What's a negative in front of this function going to do? How's that going to change things? Anyone? What's that negative out in front of the function going to do? So if I was looking at this graph and then suddenly I switched over to this graph, what's that negative going to do to the graph? How's it going to change it? Flips it over the x-axis. So which one of the remaining functions has been flipped over the x-axis? Remember, you're going to start out with this one and flip it over the x-axis. I'm thinking 2 looks pretty good, right? Yeah, okay. So that one would be 2. And the last one is going to be y equals -2 to the negative x. Now, 2 things are going to happen to this graph. The first one is you reflect it around the y-axis. The second one is you reflect it around the x-axis. So both of those. All right. Now, there's not much suspense in this one because we kind of already run out of graphs. But it does reflect this fourth one. You reflect it first around the y-axis here. So that gave us the first graph. And then when I reflect this around the x-axis, I get the fourth graph. Yay. So we're going to play that game again and try and get used to some more shifting. So let's take a look at a bunch of these graphs. We're going to compare these graphs to the graphs of y equals 3 to the x. So y equals 3 to the x versus, and let's do y equals 3 to the x minus 4. Y equals 3 to the negative x. Y equals -3 to the x. Y equals -3 to the x plus 5. And let's see, a couple more. Y equals 3 to the x plus 2 minus 5. And y equals -3 to the x minus 2 minus 2. Or plus 2. Should be plus 2. My bad. So let me switch over here. Now all these graphs have been shifted compared to this one. It's our job to figure out how they've been shifted. What you should focus in on this one is right up here. Instead of an x in the exponent, you've got an x minus 4. So plugging something into the exponent like that is going to cause a horizontal shift. The question is which way? Is that going to be to the right 4 or to the left 4? What would you think? Yeah, it's to the right by 4. Nice. Moving on down. The next one. Instead of an x, I've got a negative x. So we looked at one like this earlier. What's that negative x going to do to our graph? Well, it's not going to cause a horizontal shift. It's going to cause a reflection. But about which axis? Yeah. reflected around the y-axis. Thank you. And you can see that if you'd like. Let me kind of demonstrate that here. Let's just make this list 3. So here's 3 to the x. And you can tell what the base of your exponential function is by looking right here at x equal 1. At x equal 1, the value you get from your exponential function is going to match the base. So there you go, 1 and 3. If I reflect that, I get the same thing. I just get a mirror image around the line x equals 0 or the y-axis. They're just reflections. So good job. How about this one? Negative 3 to the x. Again, you're going to get some changing of the guard from 3 to the x. Where's this one going to get reflected around? All right, so a little competition from one of the classes down the hallway just went by. That's okay. They're missing out, right? So where'd this one get reflected around? Yeah, the x-axis. Hey. This next one is kind of a combination of a couple things. What's happening with this next one? All right, reflected around the x-axis, so we have that again. Reflected around the x-axis. And what else? Shifted to the left by 5. Good. Again, that plus 5 in the exponent is going to cause a horizontal shift, and it's opposite of what you might think initially. Shifted, thank you so much, left by 5. Let's actually look at that a little bit. Kind of look at that in stages, maybe. So I'm just going to shut these off and I'm going to put them in directly. We'll start out with y equals 3 to the x. That's that graph. And then I'll do y equals 3 to the x. And I'll also do negative 3 to the x. Negative 3 raised to the x. So that, as predicted, reflected the graph around the x-axis. So we saw that one coming. Let's add in one more thing here. And actually, you know what? I'm going to add in a couple things here. Let's add in a point. Let's add in the point 0, 1. That's on this graph. So the point that should be on this graph would be the reflection of that, right? 0, comma, negative 1. Beautiful, because all you did is you reflected around the x-axis. Last but not least, y equals negative 3 raised to the x plus 5. So where's that point gone that was here? Oops, didn't go the way I wanted because I didn't write it right. This has to be in parentheses, x plus 5. Where'd this point go? Well, it got shifted to the left by 5. And you can see it right there. To the left by 5 puts it at negative 5, comma, negative 1. So it lands exactly where I thought it was. For my Math 1150 class, which is intermediate algebra, I always make them plot that point. I'm like, okay, I want to know where that point goes. It's kind of like, I regard it as kind of like the vertex of a parabola for exponential functions. But you can see exactly where that point goes. And it's a nice, easy point to plot. Let's try a couple more here. So let me get rid of some of these. Let's get rid of that one, that one, that one, and that one. And look back here. F of x is 3 to the x plus 2 minus 5. So again, a couple things going on with this graph. What's one of them, Maggie? How's it? Left by 2. And one else. What's the minus 5 going to do? Down by 5. Nice. So left by 2, down by 5. Let's see both of those things happen. So y equals 3 raised to the x plus 2. All right, so that was shifted left by 2. You can see the point that was at 0, 1 is now at negative 2 and 1. I can't quite get it in there. Let's just do it this way. Negative 2 and 1. There we go. And then you're going to take that graph and shift it down by 5. So let's see if we can't do that. Down 5. And the point that was here is going to have what coordinates in my new graph? It was at negative 2 and 1. Where is it going to be in my new graph? Good. So if you shift it down by 5, you're going to take 1 minus 5 because you're subtracting 1 from, or 5 from the y coordinate there. So it's going to be at negative 2 and negative 4. Perfect. Just where I wanted it. Now, let me shut off these other graphs and we'll focus our attention on this one for a moment. What if I asked you for the domain and range on this one? Well, I'll help you out with the domain. The domain is everything. All right, it just, this function is defined. There's no place where there's going to be a 0 in the denominator or a negative underneath the square root. There's nothing that's going to go wrong that's going to make this function undefined. So the domain is all real numbers. How about the range? Is the range for this one all real numbers? Well, is it going to get much lower than this right here? Let's try and zoom out a little bit. Seems like it's getting closer and closer to this line, but not crossing it. And the y value is getting closer and closer to what number? Negative 5. So your range on this one would be negative 5 to infinity. Negative 5 would get a parenthesis because you're not including negative 5. Even though eventually decimal says, oh yeah, it gets to negative 5. No, it doesn't. It's just really, really close. It rounds to negative 5. It doesn't actually get there. So, do you want to try this one? Kind of the same, just a little different. Negative 3 to the x minus 2 plus 2. Find the domain and range of that one. Well, maybe you can start me out with the domain. What do you think the domain of this one's going to be? Yeah, negative infinity to infinity, or better yet, famously, script r. I like script r. But the range, you might want to look at that one a little bit. So let's take a look at that graph. Let's see, I want to type in negative, then x minus 2, and then plus 2. There you go. Let's get rid of that, and we can shut that off. So the range, that's the y values. You want to go from lowest to highest. So On the high end, it's getting close to, but never touching what number? 2. You can kind of see that and figure that in different ways. This has been flipped upside down, shifted to the right by 2, and up by 2. But because it's flipped it upside down, it's a decreasing function, and it never gets above that number 2. So its range is going to be negative infinity to 2. 2 is going to get a parenthesis on that one. Whew. There's a couple last ones that we want to knock off. These are going back to our graphing calculator. So I guess what I would suggest that I want you to know for these kinds of problems is what these kinds of things do in terms of shifting our graphs. It's helpful to know that if your base is between 1 and 0, then your graph's going to be a decaying function. It's not going to be increasing like we saw with the other ones. It's going to be decreasing like that. It's still going to pass through, we'll call it Samantha's point at 0, 1. So you got something named mathematically after you. That's good. But it's going to be decaying like that instead of increasing. Y equals 0 is our horizontal asymptote for either of these graphs, increasing or decreasing. And of course, that horizontal asymptote can get shifted. That horizontal asymptote is going to get shifted down by 5 or up by 2, depending on this. Horizontal asymptote is not going to be affected by a horizontal shift. It's only going to be affected by a vertical shift. There's a problem like this in your homework, and I just don't want you to spend a whole lot of time on it. So let me go through how to do this on a calculator. It says an investment of $6,000 is deposited into an account in which interest is compounded monthly. All right, so let's write down a few things here. Our principal is $6,000. Interest is monthly, and that interest is 7%. If it's monthly, that's telling you N. What's N in this case if it's monthly? How many times a year is monthly? 12. So, true or false? When the bank computes daily interest, if they're saying, oh, we'll compound your interest daily, they actually use N equals 360. What do you think? True or false? It is true. Even though there's 365 days in a year, the banks use 360. That goes back to centuries ago when we didn't have calculators and fun things like that. It was just easier to use 360 as opposed to 365. Whatever. It makes the tiniest bit of difference. I mean, Warren Buffett might not even notice the difference. It's so small, but it is a difference. Let's see here. And then the time is going to vary. It's going to be a lot of different things. It's going to be 2, 3, 4, 5, and 6. So 2, 3, 4, 5, and 6. So I would do this. First of all, I'd rewrite 7% as a decimal, 0.07. Make sure you knock that off, otherwise your answers are going to look ridiculous. Secondly, I'd put it into my calculator this way. 6,000 times 1 plus 0.07 divided by 12 raised to the 12 times t power. Now I'm putting a t here, but I'm actually going to use an x on my graphing calculator just because it's so much more convenient than using a t. It'll also allow me to use our table function. Use x on the graphing calculator. Okay, so we'll do that. let's clear out this. 6,000 parenthesis 1 plus 0.07 divided by 12 raised to the 12 x power. And again, you don't need to put the times there because your calculator is smart enough to do that. If you do it this way, then answering this question is simply just plugging in different values of x and getting the decimal values from this. So from here, it's just go to the table, clear out your old values, delete, 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 and then 2, 3, 4, 5, 6, whatever you want or need. You got all of them here. And of course, this is rounding a little bit more than I want. So to see those hidden values so that I can round it to the nearest penny, you're just going to put the cursor on the y value in your table and go at it like that. So nice. Nice. Last one. A bacterial culture contains 1,400 bacteria initially and doubles every hour. Find a function that models this bacteria after t hours. So let's see. That function is going to look something like this. So I'm going to call it, let's see, n of t. So the number of bacteria is going to depend on time. It's going to be 1,400, which is our initial population, times 2 to the t. So when t is 1, it doubles. When t is 2, it's doubled again. And t is 3, 4, etc. So this actually grows really, really quickly. And for giggles, let you pick a number. Number of hours in a day that you want to let this culture grow. Now, of course, that's assuming that it has unlimited resources and can grow unfettered, but let's just go with it. How many hours do you want to wait for this thing to grow? 5, 10, 24? 23? All right, so let's do 23 hours. Let's find out how much is here after 23 hours. I can guarantee you this is going to be a big number. That's probably going to be on scientific notation on your graphing calculator. So let's do 1,400 times 2 raised to the 23 power. Now, if I was going to do more of these, I'd probably set it up to do in my table value. But there you go. 1.17 times 10 to the 10th. 1.17 times 10 to the 10th. Do realize that this is what that E10 means. Is it means times 10 to the 10th power. That's a huge number. That's like 11.74 billion. So, wow. That got pretty big pretty quick. 1, 1, 7, 4, 0, 0, 0, 0, 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 decimal places. So that's where I got this from. There's actually a 4 here. Wow. Pretty big. Pretty big. Exponential growth is really, really fast. Cool. That'll do it for this one. Let's shut it down. Any last minute questions or thoughts? No? Looking good there? All right. Good luck with the stuff.